I've always found single image random dot stereograms to be quite fascinating, and of course we've all seen those magic eye books. I think I actually still have one somewhere. They were quite a fad back in the 90s. In this video I'm going to walk you through how to create one using software that I wrote. Let's start with a rundown of how the software works. The slider selects the depth for what is being drawn. It is represented by a shade of red. The palette of tools is pretty simple. You basically just draw using shapes at different layers. Be careful though, as drawing a distant layer over a closer layer is possible, but it won't look good. I'm now just drawing some rectangles in ascending layer order, hoping that it'll look good. It's a bit tedious. Sometimes it's a little tricky to make out the different layers. It's a bit messy, but should be right. It's fun just to draw shapes, then see what they look like in 3D. It's now starting to look interesting. That should just about do it, I think. The background picture is merged with the foreground picture when the stereogram is rendered. The gradient options can generate a range of standard backgrounds. The pictures are actually merged in layer order, so it produces a clean image. The background editor is very limited and relies mainly on canned functions. Images can be loaded though. Next we need to create the seed image. This is basically the random dot pattern. We start by defining a palette of 16 colours. There is an option for it to do this for you automatically to save, well, all this time. For the purpose of this video, I'm going to create them manually. Nearly there. It's best to choose colours that contrast. Because the patterns are generated mathematically, the effects can be rather clinical. The sliders here are used to apply a random offset to the colours and can help create a smoother, more random effect. The slider and tick boxes to the right provide more control over the pattern generated. It just takes a bit of experimentation to find a pattern that you like. I think that looks pretty good. Now that all the pieces are in place, let's see what it actually looks like. These three settings can be experimented with to see what creates the best effect, but I just generally leave them as they are. And there you have it, a stereogram image in 5 minutes. And here's another nice feature. I've got to admit, this is one of my favourites. That looks great. I like to make my videos fairly informative, so let's now take a look at how this actually works. Firstly, each line is processed independently This means that each line is treated in isolation. The large red circle represents a point in space. The blue line / circle represents the pixel on the screen for two-dimensional representation. The two red lines / circles represent the points that are required for three-dimensional representation of the point. These points are projected mathematically based on factors such as observer distance, eye separation, screen distance, and the actual object distance. In 3D cinema, the 2 points represent two different images that are separately projected using different optical polarity. The 3D glasses then filter the light so that the left image appears in front of the left eye and the right image appears in front of the right eye. This tricks the brain into perceiving the image in 3 dimensions. This can't actually work for single image random dot stereograms though. The reason for this is that we are working with a fixed number of pixels, for example 900. When we process the image to create 2 separate pixels for each point, we are creating 1800 pixels. We can only render half of those. This means that we have to discard half of the points that we've just created. This is actually the most complex part of the process. What we do is calculate which points to render based on layer priority. As the priority is based on distance, closer points have priority over further points. Effectively, it's hidden point removal. Arrays are used to track the distance of points, and they are used to decide whether to render a point or not. Here is the subroutine that does the work. I've added comments to explain what the variables do. First, it loops through each row separately. Next, it initializes the 2 arrays that are used for the hidden point removal. Next, it scans each pixel in the line. This is the actual calculation for the 2 new left and right points. Here, it checks whether the points are actually within the screen, ignoring any that aren't. This is the first of the 2 functions that determine whether the points are further away and updates the look left and look right arrays. This is the other. They are almost identical. It's difficult to explain how these work, but can be figured out relatively easily. If neither of the conditions for the hidden point removal were met, look left and look right are set to the calculated left and right coordinates of the pixel. Here is where it calculates the color to display. The code that uses the O variable is no longer used, but I forgot to remove it. This code renders the image. This can actually be done in the previous loop, but needed to be separate in previous versions. I first wrote this nearly 20 years ago, and it evolved from something much simpler. In the earlier versions, the rendering needed to be separate from the color calculation. This had something to do with the O variable. I will be cleaning this up. Next, a slideshow of different images. When the first one appears, get the correct position to view, then hold your eye position as the slideshow progresses. Every picture has the same view position, so you just need to get it in focus once.